So today we're going to be talking about what regular expressions are. So before I get into that, I really want to motivate where we're going with this. I'm going to stress that this is a wide topic, many applications in relation to this concept or this family of concepts. But I'm just going to be talking about what a regular expression is, and I want to layer it into the discussion we've had up to this point about regular languages. So as the name suggests, there's going to be some relationship with a couple of different things here. But I'm not going to get too deep on that, but I will give you the main inclination that regular is there for a very good reason. And we've already heard about regular operators, and we've also heard of regular languages before. So let me frame this appropriately. So when we describe or recognize. Now, note when I say describe, I also could mean define as well. Or recognize a language. We very often would describe it up to this point as indeed a formal language. But how did we recognize these languages? How could we describe a language? What if I told you it was a regular language? Depending on how we defined the regular languages previously, what would you say? Well, that means that there exists a deterministic finite automaton such that it recognizes said language. That's what we gave as our initial definition of a regular language. So there's these, what I would describe are machine-like descriptions. So we have this machine-like descriptions. So we could describe a language using a machine, right? So what are some that we've seen up to this point, just as an example? Well, I just mentioned the deterministic finite automata. So we can use DFAs to do this. We also talked about how NFAs were also going to do this. We also talked about epsilon NFAs as well. So all of these provide machine-like descriptions of languages. So if I wanted to say, come up with a way of recognizing a string in a given language, I can design a machine, and that machine, presumably if it's correct, can recognize said language, meaning that if it accepts, that means that that string, the input string, belongs to that language. If it rejects, then it does not belong to that language. And the language of the machine is a formal language. So naturally, now when you think about this, this is one way I could describe languages. Let's go back a few steps back. When I defined a language, what was a language? It was a set of strings, right? It was just a set of strings. And we also had this discussion about regular operators, right? Do you recall I talked about we talked about these things called regular operators, right? Remember we talked about these? There were some examples of operations I showed you. For example, we talked about union, we talked about concatenation, we also talked about star. Those are examples of regular operators. These are the main ones. These are what we would call regular operators. We've talked about these, but what did we apply these to? Well, we could apply these to languages, right? So if I give you a set of strings, I can apply these operations. And what did I tell you previously? Now, I didn't prove it, but what did I tell you? Is that when you perform on two languages that are namely regular, if you give you two regular languages, if I perform any one of these three operations, what happens? What kind of language do I end up with? A regular language. What if there was a simpler way for me to describe a language based on these regular operators and being able to represent languages as variables. So this is where I want to go with this. So instead of it being like a machine-like description, suppose that instead we were looking for, coming back to our formal languages, suppose we had an algebra, I'll use this comparison, an algebraic or declarative description. I'll say an algebraic or declarative definition. So meaning that just like in algebra, at least the algebra you're probably used to, where you have variables and you can describe operators within that algebra, you can have it so it applies it to numbers and it evaluates expressions, right? That's something that you're familiar with from, say, we're talking about like school grade algebra. So this is what regular languages are going to fall under. But here's the neat kicker. We can actually describe these languages using so-called regular expressions. So the analogy I want you to think about with this is, imagine you have like an algebra that you can describe sets of strings with. So regular languages with other regular languages. And as I mentioned, there's closure properties on all three of these, for example. What if I could describe to you a language, so which strings will get accepted, using an algebraic or declarative definition akin to algebra to variables and numbers. So that's what we're going to be going for with regular expressions. So let's define what a regular expression is. So you'll notice that I'm not going to be talking about machines, at least at this stage. I'm not talking about machines. Instead, what's going to happen is I'm going to give you a declarative way of talking about a language. So you can imagine, I want to describe a regular language to you. I can use one of these expressions. I haven't proven to you that this, in fact, will be a regular language, but I'm just trusting that you will follow along with me at this stage. So suppose that I want to have some way of describing a regular language to you, but doing it in a way that looks a lot more like algebra for someone like perhaps yourself. So we're going to define it inductively. So there's going to be a basis, or bases, and an inductive component. So there's going to be three cases in the bases. So these are kind of like your building blocks for a regular expression. So I'll give you the first two cases. So the first case and the second case, I'm just lumping them together because it's a little less space for us. So the first thing you need to know is I can describe as regular expressions the empty string epsilon and the empty set or empty language. These are defined as regular expressions. These are regular expressions. And these namely represent, so representing the languages. They represent the language that consists of only the empty string and the empty language, respectively. So to be a bit more precise about what I'm referring to, so if I ask what the language, so you can take one of these regular expressions and ask what language it represents. So I'm going to use notation similar to what we use for the DFAs, NFAs, and epsilon NFAs. So the language of, say, the regular expression that represents the empty string, like this. This is this set of strings, namely just one in there, the empty string, and the language of the of the regular expression that represents just the empty set or empty language is empty as well. So notice that I'm using epsilon and the empty set here. I'm using both of them as symbols for regular expressions. So please take note of that, is that these are expressions. So these are regular expressions in themselves. So it's just one symbol. So it's just one symbol, but they're each have their own special labels, okay? So empty string, that is actually the set containing the empty string, and empty set is just the empty set or empty language. So just as a note, actually no, let me give you the third one here. Naturally, I would like to have it where I can have just a set with just a symbol in it as well. If A, so if A is any symbol, so imagine you have a symbol that you would like to express, then, now to make this a little easier for us to parse, I'm going to typically use a bold-faced version of the symbol to represent that regular expression for the symbol. But because I don't boldface my characters on the board, I'm going to underline them instead. Then A is a regular expression. So just to be clear, this underlined version refers to the regular expression of the symbol A. So this is the regular expression of A. So do note in this case that the language of the regular expression for symbol A is just simply the set that contains A. That's it. That's it. So these are actually all of our cases in the bases. I must make an important remark though, because we can build more sophisticated regular expressions by introducing variables. So note that a variable such as, say, a capital L, or this could be, usually it's written as a capital letter. So this is typically capitalized. It could be like a capital A, it could be a D, it could be whatever symbol you like, as long as it's a capital letter. It makes it a little easier to distinguish from symbols, because normally you use lowercase letters for symbols, usually. But whatever this is going to represent a variable. Can be used to represent a regular language, which we'll use this in our inductive cases. So if ever you have a regular expression, we can replace the entire expression with a variable, because remember, it represents a regular language. Hence, if I give you a regular expression which has a language, right? I'm just going to take that and I can represent that as a variable. So let's now proceed to the inductive case. Sorry. So now, as I mentioned about these regular operators, so there's our regular operators over there, those are going to characterize the case inductively, because as I told you, when I take two regular languages and I apply a regular operator on them, I still end up with a regular language, right? So they're naturally going to be a part of this part of the definition with an extra case. Just more of a technicality though. We introduce regular operators. So we're going to have a case for each one of the regular operators. Plus, we're going to introduce parentheses, so we're allowing parentheses as well. Just like you'd be familiar with when you're playing around in algebra, right? So you have your like multiplication, addition, and you have like parentheses, you may have exponents and things like that. We didn't have the same kind of thing in play here. We're going to have an order of operations, and we're also going to have precedence around these parentheses. So I'll get into more details about that in a moment. So for each one of the regular operators, I'm going to define a case. So first we have union. So if I give you, suppose that I give you two regular languages. So suppose E and F are regular, like they could be regular, well, we'll call them, we'll go regular expressions. So suppose that E and F are regular expressions. Remember, it's just a variable that denotes a regular expression, which in itself has its own regular language. So suppose E and F are regular expressions. Then the union of E and F, which will be noted with this plus sign as a regular expression. So I'm just using this symbol for us here. Depending on where you're running into regular expressions, they may use a somewhat different symbol. But the point is in our discussions, we'll use this plus sign for union. Previously, we had seen it for specifically sets. This is for regular expressions. So this is a regular expression. So if I take the union of two regular expressions, so I apply a union operation. So this is a regular expression, that's a regular expression. I perform union operation. Whatever the result is still a regular expression. So where E, and I'll just refer to it as plus sometimes as an abbreviation. So where E plus F denotes the union of the language of E. So remember, E is a regular expression, and the language of F. I.e., and now I'll pull out the regular expression connection with the regular operators. I.e., the language of E plus F. So this is the resulting of our regular expression where I apply the union. This should be the language of E union the language of F, as per our discussion for regular operators. Seems pretty straightforward, right? Because this is just us giving a special name, namely the union operator, for our regular expressions. So remember, all it is just a way of describing what happens in a specific, so it's giving us a specification of the language when I can describe it like this. So suppose I had a regular expression for E, regular expression for F. If I add this plus in between the two like this, that specifies a language. It will be this language. But this is the regular expression. So next, we got concatenation. So this will feel a lot like I'm just revisiting regular operators. So EF, so I'm just not going to, sometimes you might write a dot in here explicitly, or just like literally a dot like this, but I'm just going to write them right beside each other like this. Is a regular expression where EF denotes the concatenation of the language of the expression E and the language of expression F. To be a bit more specific, the language of the concatenation of E and F is equal to the concatenation of the language of E and the language of F. So I put the dot in there just to be a little bit more specific with you because I used that notation along when I was defining regular operators. So note that I would normally write those right beside each other as well. Like that's perfectly valid as well, just as long as it's clear for the reader. So I'll just make a remark as I noted it previously. So if ever you need like a specific operator, very often explicitly say and write this as a regular expression, often it's using a dot. Usually you just write dot, like a period, as opposed to a center dot like that. So often a period is used to denote concatenation. So what I'm saying is if it's unclear what that means, just write E dot F where this is just a period. Wherever unclear. So there's case number 2. Next I have to talk about the star operator. So let's talk about the star operator next. The star. So naturally, if I give you a regular expression, if I apply the star operator to it, so I'm just going to write a star like this. This is a regular expression denoting the star or closure, wherever terminology you would like to use, the star or closure of the language of E. To be a bit more specific, the language of E star is the exact same as me saying, if I give you the language of E, so suppose it's the same, so suppose I give you the language of E, I take this and I apply the star operator as per our regular operators. That's what this is. Now next, I have to talk about parentheses because I promised you I was going to talk about those. So, how do they work? So, it's going to be a fairly simple rule, but it's a versatile one. So, what do you do with parentheses? So what happens with parentheses? So, if I give you a regular expression, I put parentheses around it. So, suppose I parenthesized the expression E. This is also a regular expression. This is also a regular expression. I notice the language of F is a little off. Let me just... That should be a bit better. So, anyways, so is also a regular expression. That says expression. It's sort of melting over there. And is the same language. It's the same language as E. i.e., suppose I ask you what the language of the parenthesized version of E is. Well, this is just the exact same as the language of E. So notice that it's just the exact same if I put the parentheses around it or if I didn't. But sometimes it's helpful to have those parentheses to help me denote or carefully specify which things are being applied to a regular operator versus which things are not. So that order of operations with the regular operators is much clearer. So let's talk a little bit about that now. So this is the definition of a regular expression. So I'm just going to make a remark about how order of operations generally works. Just big note. So this is a big note. So this will save you a lot of time. because it's a little unclear how these different operators work if you're not familiar with the regular operators. So order of operations or precedence for regular operators. For the regular operators is as follows. So star comes, so we got star first, then you got concatenation, then you got union. Or equivalently of star, concatenation, union. If you want to talk about them as languages. So that's for regular expressions, this is for regular languages. So this is kind of like the language world, this is the expressions world. So let me give you an example, what I'm referring to. So suppose I give you this regular expression. So I have 1, 0. So I'm going to have 1, 0. Suppose I define this over the binary alphabet. So suppose I have 1, 0. So I have each one of these symbols. I have concatenated. I have done some sort of concatenation here. Then I'm going to have a union operation somewhere, and then I'm going to have this the 0. Now, you might be staring at this and asking, Dan, what does that mean? It's because it's a little unclear if you're not familiar with what this should be doing. So you see there's a star operator. What is it associated with? Well, let me clarify this. So this is how you would group this. So remember, star comes first. So I'm going to use parentheses to help clarify any confusion about how this is actually grouped together appropriately. So first you see a star operator over there, right? I told you that comes first. So you do that first. But notice that it is only grouped with the 0. It is not with the 1, right? So we have 0 star, right? So the 0 is associated with the star. Next, what else did we say? We said, now we've taken care of the star. Oh, how about the concatenation? Okay, concatenation is next. So notice that the 1 is right beside the 0, star, right? And then we have the union operation. With what? The 0, right? So the expression for 0. So this is actually how, when you get used to regular expressions, this is how you might interpret this. So notice that the 0 is only grouped, like the star is only associated with the 0. It's not with 1, 0. And take note that you wouldn't apply the union operation until you've carried out that concatenation over there with the result of the star operation. So please take note of this for the grouping. And I thought I would do one example just to illustrate how you can express a language with this definition. So let's do an example. So we'll do some more examples of designing regular expressions, but I thought I would keep something nice and simple for our discussion here. So suppose, because you'll get a little bit of a feel for this. Suppose I wanted to have a regular expression that's supposed to represent all binary strings. Now, you may not have thought about this, but all binary, like a language that consists of all binary strings, that is technically a regular language. You can design a deterministic finite automaton that can recognize that, right? I'll leave that to you as an exercise. But I want to take advantage of some things you know about how these regular operators work to help build a regular expression that can that describes. So notice that instead of talking about accepting or rejecting, I'm going to talk about describing. And if the string in question is in fact one that matches the specifications of the regular expression. So in this context, I'll be describing, I'm giving you a descriptive way of characterizing all strings that, if it fits the form of the regular expression, is indeed been recognized, right? So I want to kind of start off simple before actually we get too far. So let's go through this carefully. So if I had all the binary strings, what would that look like as a regular language? So suppose I give you a language. It consists of just 0 and 1, right? So I want to walk you through step by step how we can come up with a language that would be all binary strings. How did I normally describe that to you? Well, I can have a 0 or a 1, right? Binary strings can look like this. It could be the empty string, right? It could be 0, it could be 1, it could be 0, 0, it could be 0, 1, it could be 1, 0, it could be 1, 1. You could keep doing this, right? Well, I have a 0 or a 1. What did I use to describe all binary strings previously? I'd apply a star operator to this. So let's walk through the process of how I would construct this resulting language. So how did I do it? Well, it's 0, right? There's a regular expression for 0, right? There's another regular expression for 1. Now, if I want to put 0 or 1, as I have in this set, right? You pick one of them. Or possibly none, right? But the thing is, I have to pick, I get to pick, right? So suppose I want to pick a 0 or 1. What would I do here? So please notice that the expression 0, so I have the regular expression for 0, because I have one symbol here, 0, and I have another symbol, 1. I'm going to take a union operation, right? Because remember, what are these? This is the language that consists of the symbol 0. This is the language that consists of the symbol 1, right? If I wanted to have 0, 1, just 0, 1 without the star, I would want to do a union operation to them. But this is the description of that, right? This is a regular expression for that. So this right here, what I've just written here, is the language. So if I ask what the language of this expression is, it is the language. Is the language 0, 1, where these are our symbols. So what did we do next? Like what was the next step in this process? We applied the star operator, right? So naturally, I want to apply the star operator, but I need to do it carefully. I need to use parentheses to help me do this. So applying the star operator to this expression, we get what? Well, how would I apply the star operator? Well, I want it to be such that it is encompassing all. So I want it to be just this set here, and I want to apply star like I have here. So we know that just this set without the star is, in fact, this represented by this regular expression. So all I do is I take that regular expression, group that all together, and I apply the star operator, which is going to be representing the following language. So which is the language of this expression is in fact the desired language, a set of all binary strings. So now if I give you any finite alphabet, so any alphabet, can you see how you can describe like if I write down like sigma. So we normally use this as some finite set, right? Do you see how sigma star would also be a regular language? Just to motivate this, I'll do another example just to illustrate the point. Because remember, if sigma is 0, 1 like this, it's exactly what I wrote here, right? So if I wanted to have sigma star like this, I can generalize this even further. Like suppose I gave you another set for the alphabet, A, B, C. How would I describe the set of all strings composed of the symbols here? Well, I would have a regular expression for each one of these, right? And I'd perform union operations among all of them, right? Because I want it to be able that you can pick any one of them, but do it 0 or more times, right? So sometimes when people talk about regular expressions, they sometimes will allow you to use the alphabet as a symbol. So very often this is used as a shorthand for something like, so if I, instead of writing out, say, this like this, they may write just this. So that's just one example. I thought that would start off with something nice and easy for us. But we're going to be seeing some more examples of regular expressions and designing them.